Dr. David, you talked about 2D, 3D. Let's use this time to get into the major differences in the technologies. I know there's different types of tubes or detectors, however they're referred to. They probably have different attributes, and I know that there's 2D and 3D. That's at least two of the major differentiators between specific machines. Tell me the difference between 2D and 3D, and in what application would one waste money, maybe a narrow application where one might waste money getting 3D when 2D is all that's required, and in what applications would be missed out if they only had 2D?
What I would say is that for a typical board shop, which is perhaps different from Robert's thing where he's doing failure analysis, you're going to require as a minimum a 2D inspection, a simple image, same as the broken leg in the hospital you alluded to earlier. But we also need the oblique angled view and being able to have the magnification and not lose that magnification at an angled view. Now, you said 2D and 3D, I'll come on to that, but there is this so-called 2.5D or laminography as it's known in the industry. And this is using a, forgive the language, tomographic, a CT technique, a CAT scan technique to generate layers within the board. So you can begin to separate, say, side 1 from side 2 at different layers. Now this takes more time, is more expensive as usually an add-on to these 2D systems, but potentially for LGAs that are overlapped or QFNs that are overlapped side 1 and side 2, you may not know where the voiding is. Is it at the die level? Is it at the substrate level? And whether it's side 1 or side 2. And the potential, although I would say it's a nice to have, not absolutely necessary to have, would be within a board shop to actually go and have that functionality as an additional extra. When it comes to tomography CT, CAT scans, then they can be added again as an option to some 2D systems, but for the people who are doing it for investigations and specialist applications, then they tend to be standalone systems for technical reasons that allow high precision movement of the sample and multiple images. But you're talking, rather than seconds to capture an image, you may be taking minutes or hours to actually achieve it, and you're looking at a model, and that's where the non-destructive testing for castings and things like that uses it all the time. So that's my take on it. So 2D, maybe laminography, probably for most board shops, not CT. Go to a supplier who could provide that, probably, until or unless you're doing it so often you have to take that functionality yourself.
To add a little bit more to what David has said, you know, with IPC 7095, which looks at, or at least gives specs or numbers which are acceptable for joints on an interface, it's very hard to make those measurements unless you have laminography. Simply because, you know, an angled 2D view, if you move it around a bit, you can actually work out which, we're talking BGAs, whether the voids are at the top or the bottom interface. But what you can't do is an automated void calculation, because effectively you're looking at an angle. So yeah, I mean, laminography is crucial if you're working to that kind of a spec. And my own personal opinion is laminography really in this day and age is needed, especially when we're looking at thermal planes on components where you've got densely packed double-sided boards, and the customer has given you a spec. This thermal plane has to be at a minimum of 20% voiding, because if the voids are any bigger, then you don't have the heat transfer, and if you don't have the heat transfer, the component overheats and the die cracks. So yeah, laminography is becoming a bigger and bigger deal for people.
So the so-called 2.5D is,
yeah,
sounds like that's kind of the floor. That's kind of the basic starting point that one should consider, rather than strict 2D.
The unfortunate part about the 2.5D situation is it's often portrayed by certain marketing types as true 3D, which it is not. And 3D is CT scanning, pure and simple, period, full stop. To Dr. David's point earlier, CT is expensive because it's time consuming. True CT, some of our more complex applications on things like additive manufactured parts or castings or things of that nature, we often put the part in the machine at 5 p.m. or 6 p.m., set it up, hit start and go home. And we come in the morning 8 to 10 hours later, and we have several terabytes worth of images ready for post-processing. That's what it takes. And it's available for those who wish to pay for it, but it is an expensive process because of that.
Thanks for listening to the Reliability Matters podcast. Join us on the second and fourth Tuesday of each month for new episodes of Reliability Matters.